I will be discussing cohesion, adhesion, and the electrostatic forces behind these properties. To begin, I am going to do a simple demonstration comparing different household liquids. Then we will play around and experiment with these liquids and relate what we witness with what we know about chemistry. Finally, we will discuss electrostatic force, the underlying physics property that is responsible for what we see in this video, as well as our entire universe existing the way it does. Alright, I've got my eye protection, my pandemic mask, gloves, tank top, and flip-flops. Let's start. The household liquids we will be using in the demonstration are concentrated vinegar, which is a solution made up of 30% acetic acid and water, isopropyl alcohol, which is 70% alcohol and water, and lastly, the star of the show, filtered tap water. Now, what I'm going to be doing is showing the behavior of these liquids as droplets. This experiment is very observational and qualitative. I'll be using the samples set aside here and a simple dropper to make various sized drops on 3 different surfaces. We'll start with the water because there's really no risk contaminating the other solutions because they already contain water. I'm glad I found this dropper in my house. My alternative was a baster. Using different surfaces will allow us to observe both cohesion and adhesion. For our first surface, I am using the back cover of the lab manual. It is a laminated material of some type of plastic. It's really fitting though. Next we have a strip of clean glass, and last is the edge of a plastic lid. It's kind of abrasive, so that'll be interesting. So we'll be looking at cohesive force, which is the strength of attraction between the same molecules, and adhesive force, which is the strength of attraction between different molecules. All right, let's get dropping. Here's water. We'll make some drops of various sizes. We can see very nice hemispheres form, and no movement is taking place after it forms. On the glass, the radius is comparatively larger and the height a bit lower. And on the plastic lid, pretty similar to the lab notebook surface. Now, the acetic acid solution. Pretty nice drops forming. I would describe it as a little more runny than the water. Definitely shorter and wider. And you can see some small drops splatter out. On the glass, it's a little messy looking. The drops don't seem to form even circles. On the plastic lid, pretty similar to the lab notebook. Now for the isopropyl alcohol. Already we can see it is much more runny. It looks like the drops want to form circles, but then kind of bleed over the edges. On the glass, spreading out very thin and seems to just keep moving. On the plastic lid, pretty similar to the lab notebook, but maybe a little bit shorter. So here's a view from the top. You can see a definite difference in the radii between the water and acetic acid. The alcohol takes on more of a blob. The lab notebook definitely seems to be the most hydrophobic surface. Now, due to the lack of instruments with precision, I didn't measure specific volumes of the droplets. So it should be noted that in these observations we are generalizing the comparisons. The important thing is to see the difference in behavior and shape. Now let's have some fun. Using household lamb fur, I am ionizing a plastic turkey baster. This will give the baster a temporary charge for the next observation. Electrostatic force has got to be the coolest thing ever. This is Coulomb's law, and the same force we witness in observing cohesion and adhesion. Negatives desire to be with positives, and like charges repel each other. Coulomb's law describes this force as a function of charge and the distance between two particles. Here we see how that force grows stronger as the distance decreases. And listen carefully, you can hear a pop. a spark occurred and electrons were actually transferred. The acetic acid solution sparks too. The isopropyl alcohol is reacting, but too little to really see. Now we'll add drops of isopropyl alcohol to the water and acetic acid solutions. Here we are witnessing these solutions becoming less cohesive. Remember, the force of gravity is also involved here. The molecules in the solution have mass, are being pulled down, and essentially flattening out the spherical shape. It's so cool to watch, like a blob from science fiction, as the alcohol disperses in the solution to reach equilibrium. Let's see it again in slow-mo. Let's jump over to some surface tension. The surface tension for an extremely cohesive liquid like water is awesome. The hydrogen bonds formed on the top create an extremely strong layer that can support heavy objects. We see that in the acetic acid solution, the paperclip immediately sinks. The same goes for the alcohol. Pretty amateur footage here with my hand in the way. Now, let's see how many drops of alcohol it takes to weaken the surface tension of the water sample to sink the paperclip. Usually dish liquid is used in this. About 12 drops. The last demonstration is a classic, but is one of the coolest ways to witness electrostatic force. Once again, we use our ionized turkey baster and head to the kitchen sink. Here we see Coulomb's law in action, as the force appears stronger as the baster gets closer to the water. The footage here is not sped up. My hands are just that shaky. The water seems to come in contact with the baster, and some droplets behave like fireworks. Here's another view in slow-mo. So cool. To conclude, let's look at some molecule shapes. The polarity of each molecule is how electrostatic force is able to take place. Here's isopropyl alcohol. We can see it as polar, but the carbon-hydrogen bonds are considered nonpolar. So the net dipole moment here is weak compared to water. Here is acetic acid. It is also polar, but like alcohol, has a weak net dipole moment compared to water. Finally, water. Here there are no neutral bonds. The molecule has a strong net dipole moment, and because of its size and shape, it is able to form hydrogen bonds in an extremely efficient and strong lattice. It's important to recall that all of the solutions we tested were concentrated in water, which plays such a significant role in cohesive forces. For future videos, it would be interesting to see how some pure substances behave with similar tests. That's all I have, but as always, thanks for watching, and don't forget to like and subscribe.